So today I'm gonna do this intro to deep learning course. Let's begin. I'm gonna spend just 2 hours today, and then I'll do the other two tomorrow. Welcome to deep learning. Welcome to Kaggle's Introduction to Deep Learning course. You're about to learn all you need to get started building your own deep neural networks using Keras and TensorFlow. You'll learn how to create a fully connected neural network architecture, apply neural nets to classic ML problems, regression and classification, train neural nets with stochastic gradient descent, and improve performance with dropout, batch normalization, and other techniques. The tutorials will introduce you to these topics with fully worked examples, and then in the exercise we'll explore these topics in more depth and apply them to real-world data sets. What is deep learning? Some of the most impressive advances in artificial intelligence in recent years have been in the field of deep learning. Natural language translation, image recognition, and gameplay are all tasks where deep learning models have neared or even exceeded human-level performance. Deep learning is an approach to machine learning characterized by deep stacks of computations. This depth of computation is what has enabled deep learning models to disentangle the kinds of complex and hierarchical patterns found in the most challenging real-world datasets. Through their power and scalability, neural networks have become the defining model of deep learning. Neural networks are composed of neurons, where each neuron individually performs only a simple computation. The power of neural networks comes instead from the complexity of the connections these neurons can form. So I already know all of this, so I think I'm gonna skip this part, but it's basically each hidden layer, which is a layer before the output layer, has a sigmoid function that is activated by the sum of this equation here, which is each of these inputs has a weight and some form of data and a bias. And then you multiply all of these weights and biases and sum the biases to determine whether or not the hidden layer, that neuron in the hidden layer, is going to activate. Linear unit as a model. Though individual neurons usually only function as a part of a larger network, is often useful to start with a single neural model as a baseline. Single neural models are linear models. So means that they separate data sets linearly with a line, which means that they have a binary activation function, if I'm not mistaken. Because they can't perform higher other forms of logic, which is different than when you have more. The H0 dataset has many more features than just sugars. What if we wanted to expand our model to include things like fiber or protein content? That's easy enough. We can just add more input connections to the neurons, one for each additional feature. So each one of these, I think, is a column or a feature of the dataset, the inputs. To find the output, we would multiply each input to its connection weight and then add them all together. The formula for this neuron would be the sum of the weights plus the bias, which means the bias of the neuron. A linear unit with two inputs will fit a plane, and a unit with more inputs than that will fit a hyperplane. So two inputs fits a plane, yeah, because the data has more dimensions. So the more inputs you have, the more dimensions the data has, which means that the complexity of the sets you're trying to find the boundary is higher. Linear units in Keras. The easiest way to create a model in Keras is through Keras.Sequential, which creates a neural network as a stack of layers. Create models like those above using the dense layer, which we'll learn more about in the next lesson. We define a linear model accepting three input features: sugar, fiber, and protein. and producing a single output calories, like so. Layers.ends, units 1, input shape tree. So it didn't specify here which inputs are, just set the amount to 3. First argument units, we define how many outputs we want, since we are just predicting colors. So we will use units 1. Let me just load this before I continue reading the rest. With the second argument, input shape, it occurs the dimensions of the inputs. Setting inputs to shape 3 ensures the model will accept the 3 features as inputs. The problem I was having before I started all this, when I was doing the free code camp challenges, is understanding how the inputs are computed, how to actually put the inputs, because you have to put it in numbers. So let's see if they talk about this. This model is now ready to be fit to training data. I have a feeling they won't because they're using libraries, but there's always a chance. Why is input shape Python list? Data we use in this course will be tabular data, like in Pandas data frame. We'll have one input for each feature in the data set. The features are arranged by column, so we always have input shape equals num columns. So it is a column on the data set. Using Keras uses a list here is to permit use of more complex data sets. Image data, for instance, might need 3 dimensions. Okay, so things run. How can we predict the wine's perceived quality from the physiochemical chemical measurements? The target is quality, and the remaining columns are the features. So there's 11 features. Keras dot sequential, I think. It's already imported here. Oh, maybe not. I'll try, and then if it's not, I will import it. Yeah, but it here doesn't specify. So Keras dot sequential. Or just the input shape. It's gonna ask the other things in the model here. So input shapes tree, I guess. No, I have to put the names of the columns, I think. Oh, here they, yes. Maybe it's just 3. Oh, 11 actually. Because there are 11 features outside the quality. 12 in total, the data set. And 11. Yeah, correct. Okay. Now is the Keras dot sequential thing. The imports are the same cell. So layers dot ends. Units equals 1. Which shape? Now I don't know if I need to specify it. Probably not, because we already did it on the previous cell. So what's wrong with this? So maybe I have to. That doesn't make sense. That's correct. And that's weird. So why specify on the previous song? Yeah, this is just the way that they did the exercise. So apparently you always need to specify inside the thing. Look at the weights. Internally, Keras represents the weights of a neural network with tensors. Tensor are basically TensorFlow version of NumPy array with a few differences that make them better suited to deep learning. Represents the weight of a neural network with tensors. Tensors are basically TensorFlow. TensorFlow's version of a NumPy array with few differences that make them better suited to deep learning. So imagine it's pretty much like a vector. One of the most important is that tensors are compatible with GPU and TPU accelerators. TPUs, in fact, are designed specifically for tensor computation. The model's weights are kept in its weights attribute as a list of tensors. Get the weights of the model you defined above. If you want, you could display the weights with something like print weights bias not format. So where do I get the weights? Imagine it's gonna have 11 weights because there's 11 inputs. Eleven one. Let's see if this works. Yeah, should be tensors. Model don't. I have no idea. They didn't talk about this. Setting input shape 3 would create a network accepting vectors of length 3. So I guess I need to take one of these things here on the model, but just gonna look the solution. Model dot weights. By the way, Keras represents weight as tensors, but also uses tensors to represent data. At the input shape argument, you're telling Keras the dimensions of the array you should expect for each example in the training data. I still don't understand how it takes the data. Maybe it just takes the values of the data, and when it's categorical, you have to just do one hot encoding before, and then it takes the values of the one hot encoding to build the model. But at the end, I don't understand how this becomes the sigmoid activation function. Oh, I guess it makes sense, but it's kind of difficult to imagine because, and it's kind of difficult to imagine how I would do this if it wasn't for the library, because if the category is a column, is a matrix, after the one hot encoding, then how would you perform the operations on the matrix? I guess it would become a giant equation where each matrix represents a polynomial stack that of weights and biases. But how to do that is the part that I have problem understanding. What the output of an untrained linear model? The kinds of problems work on through lesson 5 will be regression problems, where the goal is to predict some numeric target. Regression problems are like curve fitting problems. We're trying to find a curve that best fits the data. Let's take a look at the curve produced by a linear model. Probably guess that's in line. Mention that before training a model, weights are set randomly. Let me save this. Wow, for training a model, weights are set randomly. Run the cell below a few times to see the different lines produced with a random initialization. There's no coding for this exercise, just demonstration. So it builds the model with one layer and one input, then creating the graph. Input targets. And it's changing the weights each time. Because I guess it's training to fit the data each time you run. Yeah, let's go to the next one. In this lesson, we're going to see how we can build neural networks capable of learning the complex kinds of relationships deep neural nets are famous for. The idea here is modularity, building up a complex network from simpler functional units. Seeing how a linear unit computes a linear function. Now you see how to combine and modify this single units to model more complex relationships. Layers. Neural networks typically organize their neurons into layers. When collecting together, linear units having a common set of inputs, we get a dense layer. You could think of each layer in a neural network as performing some kind of relatively simple transformation. The deep stack of layers in the neural network can transform its inputs in more and more complex ways. A well-trained neural network, each layer is a transformation getting us a little bit closer to a solution. Many kinds of layers. A layer in Keras is a very general kind of thing. A layer can be essentially any kind of data transformation. Many layers, like the convolutional recurrent layers, transform data through use of neurons and differ primarily in the pattern of connections they form. Others, though, are used for future engineering or just simple arithmetic. There's a whole world of layers to discover. The activation function. So, I'm gonna talk about the sigmoid function and the rectified linear, which are basically functions where you input the result of the equation from each layer, which are the weights multiplied by inputs plus the bias. The rectifier function has a graph that's aligned with the negative part rectified to 0. Applying the function to the outputs of a neuron will put a bend in the data, moving us away from simple lines. When we attach the rectifier to a linear unit, we get the rectified linear unit, or ReLU. For this reason, it's common to call the rectifier function the ReLU function. Applying ReLU activation to a linear unit means the output becomes max 0 weight times input plus bias, which we might draw in the diagram like. Stacking the dense layers. Now to have some non-linearity, let's see how we can stack layers to get complex data transformations. The layers before the output layer are sometimes called hidden since we never see their outputs directly. Now notice that the final output layer is a linear unit meaning no activation function. That makes this network appropriate to a regression task, where we are trying to predict some arbitrary numeric value. Other tasks like classification might require an activation function on the output. Building sequential models. Sequential model we've been using will connect together a list of layers in order from first to last. The first layer gets the input, the last layer produces the output. This creates the model in the figure above. So using Carol's the sequential again, then creating 2 layers. And to specify the activation, you just use the activation rel. So I guess this is gonna create this 2 here. This first RS4, 2 inputs, and the other one doesn't have any inputs, but actually has 3, well, it has 3 units, but doesn't have input shape because it goes after the first one. I don't understand why this input shape is just 1 though. Oh, I guess there's just 2 inputs and this one is just... Not sure what this one means here. Oh, it's the bias. The bias for each one. Makes sense. So the bias is not specified here. Sure to pass all the layers together in a list. Like layer, layer, layer. So they are in a list. Oh yeah. Before here's list. Instead of as separate arguments. Add an activation function to a layer, just give it its name in the activation argument. Very easy to understand so far. I wonder if there's a way outside of books, maybe a video or a course that's for free, where they show exactly how to build from scratch without using libraries. The main doubt I have is about the input, how to convert the dataset in the dataset or whatever, trying to achieve in 2 inputs. Target for this task is the column compressor strength. That's one. The remaining columns are the features we will use as inputs. What will be the input shape for this dataset? 1, 2, 3, 4, 5, 8. Find a model with hidden layers. Now create a model with 3 hidden layers. That's gonna be carols dot sequential layers dot dense and have units. Each having 512 units. Activation plus value. Input shape 8. Then I'm just gonna do the same thing twice, I guess. This shit don't have any inputs. Be sure to include an output layer of 1 unit and 1 activation. So 3 hidden layers, each having 512 units. Should add an output layer of 1 unit and no activation. And also input shape as an argument for to the first layer. Real object has no attribute name. So the way that I did the activation is probably wrong. Oh, it's just relo. No caps lock. Correct. Let's explore activations functions some. The usual way of attaching an activation function to a dense layer is to include it as part of the definition with the activation argument. Sometimes though you want to put some other layer between the dense layer and its activation function. We see an example of this in lesson 5 with patch normalization. In this case, you can define the activation in its own activation layer. So sometimes though, you will want to put some other layer between the dense layer and its activation function. In this case, we can define activation in its own activation layer like so. This is completely equivalent to the ordinary way. Layers dense, unit state, activation rule. Write the following model so that each activation is in its own activation layer. So it's pretty much the same thing. But I just put it on a different line. Actually, copy the whole thing. Oops. I did something wrong, I think. Erase that. Well, it's actually Layers activation problem. I don't understand why would you do that, but guess they will explain on the next lessons. There's a whole family of variants of the rel activation, Alice, and Swish, among others, all of which you can use in Keras. Sometimes one activation will perform better than another on a given task, so you could consider experimenting with activations as you develop a model. Rel activation tends to do well on most problems, so it's a good one to start with. Let's look at the graphs, change the activation. So same stuff. Each iteration it changes the activation. In the first two lessons, we learned how to build fully connected networks out of stack of dense layers. First created, all of the network's weights are set randomly. The network doesn't know anything yet. In this lesson, we're going to see how to train a neural network. We're going to see how neural networks learn. As with all machine learning tests, we begin with a set of training data. Each example in the training data consists of some features, the inputs, together with an expected target, the output. Training the network means adjusting its weights in such a way that it can transform the features into the target. In the 80 zeros dataset, for instance, we want a network that can take each zero's sugar, fiber, and protein content and produce a prediction for that zero's calories. If we can successfully train a network to do that, its weights must represent in some way the relationship between those features and the target as expressed in the training data. In addition to the training data, we need two more things. A loss function that measures how good the network's prediction are, an optimizer that can tell the network how to change its weights. The loss function. We've seen how to design an architecture for a network, but we haven't seen how to tell a network what problem to solve. This is the job of the loss function. Loss function measures the disparity between the target's true value and the value of the model that the model predicts. Different problems call for different loss functions. We have been looking at regression problems, where the task is to predict some numerical values. Colors in 8 series, weighting in red wine quality. Other regression tasks might be predicting the price of house or the fuel efficiency of a car. A common loss function for regression problems is the mean absolute error, or MA. For each prediction, y pred may. So it's pretty much the same stuff from the other course. Besides MA, other loss functions you might see for regression problems are the mean squared error or the Hilbert loss. During training, the model will use the loss function as a guide for finding the correct values of its weights. Lower loss is better. In other words, the loss function tells the network its subjective. The optimizer, stochastic gradient descent. We described the problem we want the network to solve, but now we need to say how to solve it. This is the job of the optimizer. The optimizer is an algorithm that adjusts the weights to minimize the loss. Virtually all of the optimizer's algorithms used in deep learning belong to a family called stochastic gradient descent. They're iterative algorithms that train a network in steps. One step of training goes like this. Sample some training data and run it through the network, measure the loss, and then use the optimizer. So the cost function measures the distance, and the gradient descent uses derivatives and the chain rule to find the distance between the error, and the prediction. Then just do this over and over until the loss is as small as you like, or until you won't decrease any further. Each iteration sample of training data is called a mean batch, or often just batch, while a complete round of the training data is called an epoch. The number of epochs you're training for is how many times the network will see each training example. Animation shows the linear model from lesson 1 being trained with SGD. The pale red dots depict the entire training set, while the solid red dots are the mini batches. Every time SGD sees a new mini batch, it will shift the weights, W the slope, and B the y-intercept towards their correct value on that batch. Batch after batch, the line eventually converges to its best fit. You see that the loss gets smaller as the weights get closer to their true values. Learning rate and batch size. Notice that the line only makes a small shift in the direction of. So I think here is going to talk about this step, which is how much do you want it to convert or to change after it applies the descent, when it's applying the gradient descent. Adding the loss and optimizer. After defining a model, can add a loss function optimizer with the model's compile method. So Adam, let's see what Adam is. Fortunately for most, it won't be necessary to do an extensive hyperparameter search to get satisfactory results. Adam is an SGG algorithm that has an adaptive learning rate that makes it suitable for most problems without any parameter tuning. It is self-tuning in a sense. Adam is a great general purpose optimizer. So I'm gonna search this to watch later. Yeah, I'll look at this later. Notice that we are able to specify the loss and optimize it with just a string. And also access this directly through the Keras API if you wanted to do tuning parameters, for instance, but first the defaults will work fine. The gradient is a vector that tells us in what direction the weights need to go. More precisely, it tells us how to change the weights to make the loss change fastest. We call our process gradient descent because it uses the gradient to descend the loss curve towards a minimum. Stochastic means determined by chance. Our training is stochastic because the mini batches are random samples from the dataset. So yeah, there's different ways also to use this. One of them is mini batches. The others are online learning, where you just take it's not random. You're just taking every piece of the dataset, if I understand correctly. And then you have batches, which are uh, the same version as mini batches, but with larger samples each iteration, I guess. Now know everything we need to start training deep learning models. So let's see it in action. We use the red wine, call it its dataset. The dataset consists of physiochemical measurements from about 1600 Portuguese red wines. Also included is a quality rating for each wine from blind taste tests. How well can we predict a wine's perceived quality from these measurements? We've put all of the data preparation to this next hidden cell. It's not essential to what follows, so feel free to skip it. One thing you might note for now though is that we've rescaled each feature to lie in the interval 0, 1, as we'll discuss more in lesson 5. Neural networks tend to perform best when their inputs are on a common scale. How many inputs should this network have? You can discover this by looking at the number of columns in the data matrix. So it's going to be 10. Well, so the input's not on the shape. We've chosen 3-layer networks with over 1500 neurons. This network should be capable of learning fairly complex relationships in the data. Designing the architecture of your model should be part of a process. Start simple and use the validation laws as your guide. You learn more about model development in the exercises. After defining the model, we compile in the optimizer and loss function. Now we're ready to start the training. We've told Keras to feed the optimizer 256 rows of the training data at a time, the batch size, and should do that 10 times all the way through the dataset, the epochs. So let me see if I understand. So here is specifying the batch size and the epochs. So this part is the design of the layer. First, it chooses the hidden layers, how many neurons are gonna have, how many units. Then the optimizer and loss function. Then when it's training, it's gonna decide. Oh, it's gonna decide how many inputs of the data the columns is gonna get at a time. I think online learning gets one input at a time and just iterates constantly and is not random. And then when I have batch and stochastic, it means that it takes batches or many batches, like the name says, from each column, each time, each iteration, randomly. Now, I guess I gotta know how it works. You can see that Keras will keep you updated on the loss as the model trains. Often a better way to review the loss, though, is to plot it. The fit method, in fact, keeps a record of the loss produced during training in a history object. We convert the data to append data frame, which makes plotting easy. So, history df, the history. So this history is already created. Oh no, it's the name they chose here for the training thing. Model.fit, xtrain, ytrain. And where did they separate the data there? I guess this already separates the data automatically, unlike random forest regressor, where I have to separate it before. I guess at the beginning, when I first started doing these courses, I confused random forest with deep learning, this stochastic gradient descent. So I'm gonna have to look at some videos to understand better.
Hello,
I
people.
was already opening them up to understand what's the difference between random forest regressor and this one. So here's just plotting through the data frame and showing the loss column. Notice how the loss levels off as the epochs go by. The loss levels off as the epochs go by. The loss curve becomes horizontal like that. It means that the model has learned all it can. There would be no reason to continue for additional epochs. Oh, I forgot to put the timer down. Forgot to play. I guess I can look on the stream to see. Yeah, 46 minutes. Still won't have 1 hour and 50. Let's put 50. Maybe I can finish this today. The fuel economy dataset, your task is to predict the fuel economy of an automobile given features like its type of engine or the year it was made. Your processor, may call transform, standard scalar. So here is using a preprocessor before. And is one hot encoding. Log transform targets instead of standardizing. Take a look at the data if you like. Our targets in this case is the FE column, and the remaining columns are the features. So there is no FE column here. But in Excel to define the network we will use for this task. No, it's removed. That's why it doesn't show up on the data. Then here is feeding this preprocessor on the data, which means the data set, which means you will one hot encode the columns and standardize them and log them so they are all between 0 and 1. Add loss and optimizer. Before I train the network, we need to define the loss and optimizer we will use using the model's compile method. I think it was a list that I'm supposed to do. And the optimizer. And then something like that. Oh, so invalid syntax. It's the other way around. And it's not a list. It's not supposed to be on a list. Let's see if this works. Also, it doesn't matter the order, I guess. Train model. Once you've defined the model and compiled with a loss and optimizer ready for training, train the network for 200 epochs with a batch size of 128. Input data is X with target Y. So it's gonna be model.fit. Now I think it's a list. And now I have to look at the tutorial because I forgot. So X, right? Then I think it's batch 128. Box 200. Batch size. So maybe there's no validation data here. Let's try to. Or maybe it's not. Yeah, it's not on the list. Well, actually, try like this first. X string is not defined. So here is gonna be X and Y, I guess. That's the thing though. There's no X valid and Y valid as well. So since they didn't tell me to split the data, I'm guessing it's supposed to train on the whole data. Correct. Last step is to look at the loss curves and evaluate the training. When the cell loads, you get a plot of the training loss. Just putting into a data frame and plotting the column of the loss. Evaluate training. If you train the model longer, would you expect the loss to decrease further? No. Uh, Depend on how the loss has evolved during training. The learning curves have leveled off. There won't usually be an advantage. Yeah, whatever. With the learning rate and the batch size, you have some control over how long it takes to train a model, how nice the learning curves are, how his model loss becomes. To get a better understanding of these two parameters, we'll look at the linear model. Are P simplest neural networks. Having only a single weight and bias, it's easier to see what effect a change of parameter has. Next, I will generate an animation like the one in the tutorial. Change the values for learning rate, batch size, and num examples. How many data points, and then run the saw. It may take a moment or two, try the following combinations, or try some of your own. So I have learning rates, batch size, and number of examples. Hmm. I don't think I'm gonna do this because I think I already understand how it works. Then I'm gonna check and save. Well, we saw the smaller batch size gave nicer updates and loss curves. This is because each batch size is a small sample of the data, so there's more randomness. Smaller learning rates make the updates smaller and the training takes longer. Yeah. So how long? Let's see. I think I'm just halfway through now. It's four. Yeah, there's three more. Three more to go. Recall from the example in the previous lesson that Keras will keep a history of the training and validation loss over the epochs that it is training the model. This lesson we're going to learn how to interpret these learning curves and how we can use them to guide model development. Particularly, we examine at the learning curves for evidence of underfitting or overfitting. Interpreting the learning curves. You might think about the information in the training data as being of two kinds, signal and noise. The signal is the part that generalizes, the part that can help our model make predictions from new data. The noise is the part only true of the training data. Part that it is only true of the training data. Noise is all of the random fluctuations that comes from the data in the real world, or all of the incidental, non-informative patterns that can't actually help the model make predictions. Noise is the part might look useful but really isn't. I think I'm gonna skip this because I already know this stuff. Training loss will go down either when the model learns signal or when it learns noise. The validation loss will go down only when the model learns signal. Whatever noise the model learned from the training set won't generalize to new data. So when a model learns signal, both curves go down. When it learns noise, the gap is created in the learning curves. It says that the gap tells us how much noise the model has learned. Ideally, so this is overfitting, this is underfitting. Ideally, we would create models that learn all of the signal and none of the noise. This will practically never happen. Instead, we make a trade, can get the model to learn more signal at the cost of learning more noise. As long as the trade is in our favor, the validation loss will continue to decrease. At a certain point, however, the trade can turn against us, the cost exceeds the benefits, and the validation loss begins to rise. So it's pretty much saying that the more you train, the higher the chance of overtraining, overfitting, because it's getting adapted to the specific data set. Capacity. A model's capacity refers to the size and complexity of the patterns it is able to learn. For neural networks, this will largely be determined by how many neurons it has and how they are connected together. If it appears that your network is underfitting the data, you should try increasing its capacity. Increase the capacity of a network either by making it wider, more units to existing layers, or by making it deeper, adding more layers. Wider networks have an easier time learning more linear relationships, while deeper networks prefer more nonlinear ones, which is better. Which is better just depending. Which is better just depends on the data set. I'm gonna load the exercises or keep reading. So capacity is pretty much the parameters, because the more hidden layers you put, the more complex the boundary that's able to find becomes. Early stopping. We mentioned that when a model is regularly learning noise, validation loss may start to increase during training. To prevent this, we can simply stop the training whenever it seems the validation loss isn't decreasing anymore. Interrupting the training this way is called early stopping. Once we detect that the validation loss is starting to rise again, we can reset the weights back to where the minimum occurred. This ensures that the model won't continue to learn noise and overfit the data. Training with early stopping also means we're in less danger of stopping the training too early, before the network has finished learning signal. So besides preventing overfitting from training too long, early stopping can also prevent underfitting from not training long enough. Just set your training epochs to some larger number, more than you need, and the early stopping will take care of the rest. Adding early stopping. Keras will include early stopping in our training through a callback. Callback is just a function you want to run every so often when the network trains. The early stopping callback will run after every epoch. Keras has a variety of useful callbacks predefined, but you can define your own too. So it's just another method in the library. Minimum amount of change should count as an improvement. How many epochs should wait before stopping? It's our best way. True. These parameters say if there hasn't been at least an improvement of 0.001 the validation loss over the previous 20 epochs, then stop training and keep the best model we found. It can sometimes be hard to tell if the validation loss is rising due to true refining or just due to random batch variation. Parameters allow us to set some allowances around when to stop. As we'll see in our example, we'll pass this callback to the fit method along with the loss and optimizer. Train a model with early stopping. Let's continue developing the model from the example in the last tutorial. We increase the capacity of the network, but also add an early stopping callback to prevent overfitting. Here's the data path again. Now let's increase the capacity of the network. We will for a fairly large network, but rely on the callback throughout the training once the validation loss shows signs of increasing. Let me load this stuff. So callback start early stopping, being delta, patience, star best mates, true. Grace the network, model compile. Seems pretty simple. After finding callback, edit it as an argument in fit. You can have several, so put it in a list. Choose a large number of epochs when using early stopping, more than you need. So X string, Y string, validation, batch size, epochs, then callback, verbose, turn off training log. Okay. And sure enough, cars stop the training before the full 500. Okay, so it's loading, importing everything, making X equals the data frame, a copy of the data frame, and dropping the values, taking the track out of the data frame, and making the target, the column. Then futures num, futures category, using one hot encoding for the futures category, and the standard scalar for the numbers. We'll do a group split to keep all of an artist's song in one split or the other. This is to help prevent signal leakage. Group split should keep all of an artist's song in one split or the other. So it's just so it doesn't overtrain. So XY group trans size. That's pretty much a function that splits the data, but I don't understand it really well. I guess group shuffle split is a method. Yeah, from a scalar. Then after it splits, then uses in the preprocessor to transform X. So it scales to zero and to values ranging from 0 and 1. Then doing the same for X valid. It's fitting the transform for X string and then applying it on X valid. The same steps from previous courses, I guess. Just a slightly different because of this function here. Popularity is on a scale 0 to 100, so this rescales to 0. Yeah. Input shape equals X train dot shape 1, which is the shape of the columns of the data set, which is 18. Let's start with the simplest network. A linear model. This model has low capacity. Run the sum. Without any changes, should train a linear model on the Spotify dataset. So just one layer with the optimizer Adam, loss function MA. Next and train data, batch size 412, epochs 50, verbal 0. There's no callback function, which I already forgot. Let me look again. Early stopping. Yeah. Callback early stop. It's not uncommon for the curves to follow a hockey stick pattern like you see here. This makes the final part of the training hard to see. Let's start at epoch 10 instead. I think. What do you think? Would you say this model is underfitting, overfitting, just right? So let's think. Validation loss is lower than the loss. So what does that mean? So I think it's overfitting. That would be my guess. It's quite small and the validation loss never increases. So it's more likely that an arc is underfitting than overfitting. Be worth experimenting with more capacity to see if that's the case. Oh yeah, makes sense because it's just one epoch, actually. One one layer. Well, it's a simple network, so makes sense that you would underfit. So when the losses are higher, and the validation loss is underfitting. The other way around is overfitting. Now let's add some capacity to our network. We'll add three hidden layers with 128 units each. When the next touch train, the network can see the learning curves. So there's three layers with different units. They're both using artificial ReLU. Now it's overfitting. Now the validation loss begins to rise very early, while the training loss continues to decrease. This indicates that the network has begun to overfit. At this point, we would need to try something to prevent it, either by reducing the number of units or through a method like early stopping. We'll see another in the next lesson. I think I'm gonna go back to this just to understand this validation training, how it's separated. To accurately assess a model's performance, we need to evaluate it on a new data, on a new set of data, the validation data. You could see our lesson model. Yeah. When we train a model, we've been plotting the loss on the training set epoch by epoch. Should this will add a plot the validation data to. Should this will add a plot to the validation data. These plots will call the learning curves. To train the deep learning models effectively, we need to be able to interpret them. Not the training loss will go down either when the model learns signal or when it learns noise. The validation loss will go down only when the model learns signal. Whatever noise the model learned from the training set won't generalize to new data. So the blue line is the line that represents the loss function on the training data. I get it now. So it's basically splitting the data, then each line represents a section of the data that the algorithm is running. But I don't understand still, and I don't think they explained how is this epochs performed. If you first you set the weights on the training data, and then you run again, and that's the validation curve, or if you run them both, it makes more sense that you would train first and have the weights on the training data, and then run the same weights on the validation. But I'm not sure that's the case. It has to be the case actually. We'll go down only when the model learns signal. Ideally, we would create models that learn all of the signal and none of the noise. Yeah, so I assume that's how it works. So here it trained and the loss went really up, really down, but the validation is still. But that why would that be under overfitting? Oh, it's because it's showing a very low validation, but a very low loss for the training, but it still has a very high loss for the validation. And here it never learns. I still kind of not kind of sure if I get it. What's going on here? I don't understand how this represents underfitting. The validation loss begins to rise very early, while the train loss continues to decrease. This indicates that the network has begun to overfit. The gap between these curves is quite small and the validation loss never increases. So it's more likely that the network is underfitting than overfitting. Finally, stopping callback. Now define another stopping callback that waits 5 epochs, patience, for a change in validation loss of at least 0.01 mean delta. So I guess it's early stopping. I think it might be a callback. Something like that. I'm not really sure. I have to look at it. I forgot. Callbacks dot early stopping. So that part is correct. Delta patience now, probably. Yeah. Keeps the weights with the best loss. Uh, I was trying to remember my memory. Well, can't remember. It was true. So it doesn't have it's not on the list. Now run this cell to train the model and get the learning curves. Notice the callbacks argument in model.fit. Yeah, which is this thing here. So it's still overfitting, maybe. Train interpret. Was this an improvement compared to the training without early stopping? So here 12. Yeah, it was. But still doesn't solve anything in my mind. Early stopping callback did stop training once the network began overfitting. Moreover, by including restore best weights, still got to keep the model where the validation loss was lowest. Maybe what I should really look for is how to how to inspect libraries on Python using PyCharm or something like that. So then I can import these libraries and then I can research the functions one by one and see how they are designed. I think that would be a good strategy to understand how it's working behind the scenes. So instead of using the libraries, I can look at the functions that the libraries are calling and see how they are structured. It should probably take me a lot of time because it's probably very complex, I would assume. There's more to the world of deep learning than just dense layers. There are dozens of kinds of layers you might add to a model. Try browsing through the Keras docs, for example. Some are like dense layers and define connections between errors, and others can do pre-processing or transformations of other sorts. This lesson we'll learn about the two kinds of special layers, not containing any narrows themselves, but they add some functionality that can sometimes benefit a model in various ways. Both are commonly used in modern architecture. Dropout. The first of these is the dropout layer, which can help correct overfitting. In the last lesson, we talked about how overfitting is caused by the network learning spurious patterns in the training data. To recognize these spurious patterns in the network, we will often rely on very specific combinations of weights, a kind of conspiracy of weights. Being so specific, they tend to be fragile. Remove one, and the conspiracy falls apart. This is the idea behind the dropouts. To break up these conspiracies, we randomly drop out some fraction of a layer's input units every step of training, making it much harder for the network to learn those spurious patterns in the training data. Instead, it has to search for broad, general patterns whose weight patterns tend to be more robust. You could also think about dropouts as creating a kind of ensemble of networks. The predictions will no longer be made by one big network, but instead by a committee of smaller networks. Individuals in the committee tend to make different kinds of mistakes, but be right at the same time, making the committee as a whole better than any individual. Familiar with random forests as an ensemble of decision trees is the same idea. Gathering a dropout. In Keras, the dropout rate argument rate defines what percentage of the input units to shut off. Put the dropout layer just before the layer you want the dropouts applied to. So you're supposed to put it on the sequential, on the building of the model. And I guess I understand what's happening. By 30% dropout to the next layer. You're trying to make the even though you're trying to make the network learn, you don't want it to be uh, condensed or trapped in some patterns in the data. Batch normalization. Next special layer we will look at performs batch normalization or batch norm, which can help correct training data that is lower and unstable. Neural networks is generally a good idea to put all of your data on a common scale versus something like scikit-learn standard scalar or min-max scalar. The reason is that SGD will shift the network weights in proportion to how large an activation the data produces. Features that tend to produce activations of very different sizes can make for unstable training behavior. Now now if it's good to normalize the data before it goes into the network, maybe also normalizing inside the network would be better. Maybe also normalizing would be better. In fact, we have a special kind of layer that can do this, the batch normalization layer. The batch normalization layer looks at each batch as it comes in. First normalizing the batch with its own mean and standard deviation, and then also putting the data on a new scale with two trainable rescaling parameters. Batch norm, in effect, performs a kind of coordinated rescaling of its inputs. Most often, batch norm is added as an aid to the optimization process, though it can sometimes also help prediction performance. Models with batch norm tend to need fewer epochs to complete training. Moreover, batch norm can also fix various problems that can cause the training if you get stuck. Consider adding batch normalization to your model, especially if you have trouble adding batch normalization. It seems so much the same thing as adding the other one, which is the dropouts. Just with after the layer you want, or between a layer and its activation function. Mm. And if you add it as the first layer of your network, it can act as a kind of adaptive preprocessor, standing for something like scikit-learn standard scalar. So it's pretty much normalizing the data, but instead of doing all at once, doing according to the batches that are going to be trained. Let's continue developing the red wine model, and we increase the capacity even more. With that dropout should control overfitting and batch normalization to speed up optimization. This time we will also leave off standardizing the data to demonstrate how batch normalization can stabilize the training. When adding dropout, you may need to increase the number of units in your DNS layer. When adding dropout, you may need to increase the number of units in your DNS layer. Yeah, because it's gonna drop out, so it makes sense. From time to time. So dense dropouts, batch normalization. There's nothing should change this time in how we set up the training. You typically get better performance if you standardize your data before using it for training. We were able to use the raw data at all. However, it shows how effective batch normalization could be on more difficult data sets. So it's the same example as before, I guess. You choose them, category preprocessor, then splitting the data. Use the last model from exercise 4. Add two dropout layers, one after the dense layer with 128 units. I think is dropouts. Rates 0.03, something like that. And one after the dense layer with 64 units. Set the dropout rate on both to 0.3. So dropout is capitalized. Or 0.3. Now run this next cell to train the model, see the effect of adding dropout. So training is the same thing, but now the model is already built with the dropout stuff. This is a compiler graph. Oh, so it was just loading. Evaluate dropouts. Go from exercise 4 that this model tended to overfit the data around epoch 5. Did adding dropouts seem to help prevent overfitting this time? Kind of, yeah. In the learning curves, you can see that the validation loss remains near a constant minimum, even though the training loss continues to decrease. So you can see that adding dropout did prevent overfitting this time. Moreover, by making it harder for the networks to fit spurious patterns, dropout may have encouraged the network to seek out more of the true patterns, possibly improving the validation loss some as well. Now we switch topics to explore how batch normalization can fix problems in training. Load the concrete data set. We want to do standardization this time. This will make the effect of batch normalization much more apparent. It's a different data set. And compressive strength is the target. And the following cell to train the network on the unders, unstandardized concrete data. So this is the normal situation. HD is more sensitive to differences of scale. So why is not showing? Did you end up with a blank graph? Trying to train this network on this dataset will usually fail, even when it does converge due to a lucky weight initialization. It tends to converge to a very large number. Add batch normalization layers. Batch normalization can help correct problems like this. Add 4 batch normalization layers, one before each of the dense layers. So one before. Remember to remove the input shape argument to the new first layer. So I think I'm supposed to. I don't understand. What do they mean by that? But maybe I'm supposed to put it here. 1, 2, 3, 4. I think this is what they mean. Maybe. Yeah, correct. Run the next cell to see if batch normalization will let us train the model. Evaluate batch normalization. So I think I will be able to finish this today. It's taking a lot less than I thought it would. So yes, it did help. I still haven't decided though which one I'm gonna do first, the physics thing or the because are this artificial intelligence, the exploration of the libraries, because I think they are nice complement to each other. They're pretty much they pretty much involve the same concepts, and to increase the understanding on physics and the way that things relate to each other is gonna probably make me it's gonna probably make it more likely that it's a lot easier for me to understand what direction I want to go with the artificial intelligence thing. But at the same time, too much theory, if I only stay on the physics, I might like the practice. So it's probably gonna be better to go back and forth between the two, I guess. So far in this course, we learned about how neural networks can solve regression problems. Now we're going to apply neural networks to another common machine learning problem: classification. Most everything we learned about up until now still applies. The main difference is in the loss function we use and in what kind of outputs we want the final layer to produce. Classification into binary classification into one of two classes is a common machine learning problem. You might want to predict whether or not a customer is likely to make a purchase, whether or not a credit card transaction was fraudulent, whether deep space signals show evidence of a new planet or a medical test evidence of a disease. These are all binary classification problems. In your raw data, the classes might be represented by strings like yes and no or dog and cat. Before using this data, you assign a class label. One class will be 0 and the other will be 1. Assigning numeric labels put the data into a form of neural networks use. Accuracy and cross entropy. Accuracy is one of the many metrics in use for measuring success on a classification problem. Accuracy is the ratio of correct predictions to the total predictions. A model that always predicted correctly would have an accuracy score of 1. All else being equal, accuracy is a reasonable metric to use whenever the classes in the dataset occur with about the same frequency. Problem with accuracy and most other classification metrics is that it can't be used as a loss function. SGD needs a loss function that changes smoothly, but accuracy being a ratio of counts changes in jumps. So we have to choose a substitute to act as the loss function. The substitute is the cross entropy function. Now recall that the loss function defines the objective of the network during training. With regression, our goal was to minimize the distance between the expected outcome and the predicted outcome. We chose MAA to measure this distance. For classification, what we want instead is a distance between probabilities, and this is what cross entropy provides. Cross entropy is a sort of measure for the distance from one probability distribution to another. The idea is that we want our network to predict the correct class with probability 1. The further away the predicted probability is from 1, the greater will be the cross entropy loss. Technical reasons we use cross entropy are a bit subtle, but the main thing to take away from this section is just this. Use cross entropy for classification loss. Other metrics you might care about, like accuracy, will tend to improve along with it. Making probabilities with the sigmoid function. The cross entropy and accuracy functions both require probabilities as inputs, meaning numbers from 0 to 1. To convert the real valued outputs produced by the ancillary into probabilities, we attach a new kind of fluctuation function, sigmoid. Example, binary classification. The ionosphere dataset contains features obtained from weather signals focused on the ionosphere layer of the Earth's atmosphere. Task is to determine whether the signal shows the presence of some object or just empty air. We define our model just like we did for the regression tasks, with one exception. In the final layer, we include sigmoid expansion so that the model will produce class probabilities. Yeah, it's still not gonna talk about how the conversion of the inputs is made into how the calculations are made inside of Python with NumPy and pandas, I think. No, NumPy, yeah, probably just NumPy. To turn everything into a matrix and vectors, and how does this scale the. One of the things I was having the most difficult when I was trying to build it without using any libraries is finding the correct dimensions of the matrices to go back and forth on the loss function and the gradient descent. And that's one of the things I want to understand how the libraries are doing that. Add a cross entropy loss and accuracy metric to the model with its compile method. For two-class problems, be sure to use binary versions. Problems with more classes will be slightly different. The Adam optimizer works great for classification too, so stick with it. Modern this particular problem can take quite a few epochs to complete training, so we include an early stopping callbacks for convenience. I'm gonna open this up already. Early stopping carols, callbacks that early stopping, restore best ways through. Then just train the model like we did before. So just one more argument on the compile part, and using the so it's using relu on the first two and only on the output using sigmoid, because sigmoid is gonna give an output between 0 and 1, which is the probability of the thing being either one thing or the other. We'll take a look at the learning curves as always, and also inspect the best values for the loss in accuracy we got on the validation side. Remember that early stopping will restore the weights to those that got these values. So it's plotting the accuracy and the loss, the training function. For some reason it's not loading. So I think this is the last exercise. Yeah. So it took a lot less than I thought, than they said it would. They say 4 hours there. Maybe it's because I kind of skip through some parts that I already knew in the tutorials. So to me, this part is the most difficult part of this, which is organizing the data to run the model. Here is making a pipeline, simply put strategy constant, and scaling the data, and using the hot encoder to the categorical ones. Preprocessor, make column, transformer, transformer none, transformer, futures none. Then I applying this transformer to the futures. Ensure classes are evenly represented across splits. Find a model. The model we use this time will have both batch normalization and dropout layers. Choose reading with broken diagram into blocks, but you can define it layer by layer as usual. Find a model with an architecture given by this diagram. It's going to be Sequential. Keras, no, what's Keras? No, layers dot batch normalization input shape equals input shape, which is defined there, here. The number of the columns of the dataset. Layers dot dense units 356 duration zero, then batch normalization again. Then dropouts. Weights 0.3. Then layers again. 256 activation. So it's the same thing as before. After the dropouts, just another layer of batch drop, and then one activation, one output there. Sigma function as activation. Okay, correct. Add optimizer, so model.compile. No, I don't remember, but I think it's just loss equals MA. Optimizer equals Adam. And I forgot the metric. Oh, choose binary versions of the cluster entropy loss and accuracy metric. And we'll look in the tutorial. Metrics equals binary accuracy. I rather type it so it's more likely that I will remember. Binary accuracy. Well, it should be binary cross entropy gave him MA. Okay. Finally, run the cell to train the model and view the learning curves. May run for around 60 to 70 epochs, which could take a minute or two. Okay. So early stopping, defining the early stopping here, patience. 5, mean delta 0.01. Then defining the model. Train, evaluate, conclusion. What do you think about the learning curves? Does it look like the model under fit or overfit? Was the cross entropy loss good standing for accuracy? Congratulations, you've completed Kaggle's introduction to deep learning. With your new skills, you're ready to take on more advanced applications like computer vision and sentiment classification. Why not try one of our getting started competitions? Classify images with TPUs and pedals to the metal. Great art with gens. Yeah, the training, the using all these libraries, the training part is the easiest. Most difficult thing is separating the data. So let me check now. Though we can see the training loss continue to fall, the early stopping callback prevented any overfitting. Moreover, the accuracy rose at the same rate as the cross entropy. Wow. So it appears that minimizing cross entropy is a good setting. All in all, it looks like this training was a success. So preparing the data is the hardest part, and then building the model is easy if you use the libraries. The issue is that I don't want to be limited by the libraries because there might be different ways to build other networks that work better. And if you just use the libraries, you'll never be able to do that. So I think it's better to investigate how it works behind the curtain and try to build my own models instead. But I think it might be better to become good at applying the models that already exist first with the libraries because it's easier. So I'm gonna wait for this to save. But I think this is it for this course. And didn't even take took 2 hours. I guess it takes long. It's taking longer to save because of the training training parts. Whatever. Okay. So this is it. I'm gonna continue with the list on the courses next time. Yeah, I'm gonna do computer vision next. So see you then.